Hello, my name is Jason Chanko and I'm the Applications Marketing Manager at Siglent Technologies North America. In today's video, we're going to take a look at connectors, adapters, cabling, and cleaning, and how all of those can affect your measurement stability and reliability, especially when it comes to using a vector network analyzer and those types of measurements for that instrument. First, just briefly look at some of the major topics here. We want to take a look at the condition of the mating surfaces for all of our adapters and cables, as well as our instrument inputs. This is usually a visual check, and we're going to possibly use a microscope if we want to take a closer look at those surfaces. We're looking for physical changes such as scratches, gouges, or dirt that can change those electrical measurement characteristics. Do the petals of the female connectors touch? Are they making good contact with the conductors? We also want to clean using an electronics grade IPA or isopropyl alcohol, lint-free swabs and cloths, and then we also want to have some dry, clean, compressed air available. We can also take a look at the center conductor height and concentricity of our connectors. There are special gauges available for that. And then there's the depth of dielectric and connector mating surfaces, again, also available with some special depth gauges. We're not going to go into detail of that, but I did want to bring it up because it is very important. Here you can see the concentricity and some of the measurements, physical measurements that we may need to make on a specific type of adapter or connector. Here we've got a Siglent F604FS female calibration kit. This is a 3.5 millimeter. Each of them short open and load elements have a cap. We want to remove that rubber element, and you can see with the 3.5 millimeter there is air as the dielectric between the center conductor and the outer. We've got some gold plating or metallized plating to help longevity. Here we've got some lint-free swabs. Unfortunately, I don't have any cloths with me today, but we're going to put some isopropyl alcohol on and we're going to swab around the interior of that connector, that center conductor, and also the threads. We could also use the tip of the swab here to get into the threads, or we could use a lint-free cloth. And after we've cleaned, we can take our compressed air and we can give that a quick shot just to blow off any of that residue from the IPA or the isopropyl alcohol and get any dust off of it. Now we can replace the cap if we're not going to use it right away. And I do suggest keeping the caps handy. They are really nice and do all of the connectors as well as the through adapter. And then we can just cinch that back up if we're not going to use them right away. When we go to our cable, in this case we're looking at an N-type connector. We can also pull that cap and you'll see we've got that center conductor, which is gold color or copper color. And then we've got the dielectric around that as well as that ground plane. And so we're going to want to clean all of those surfaces. Again, we'll have that swab. We're going to go around the center conductor and dielectric. And we want to check and just make sure that center pin is aligned and in the center. And we can then clean around. We can swirl that swab as well. And we can clean that inner thread and the inner mating surfaces just to make sure that we don't have any dust or any big particles in there as well. Quick observation visually. And then we can hit it with that compressed air again just to get rid of any dust that we might have knocked loose. And we can replace the cap if we need to. Now we'll go to the other end. This cable terminates in an SMA connector. The differences between SMAs and 3.5 millimeter, you can see that this SMA has a Teflon dielectric around the center conductor, right there, that white material. And then that can get quite dirty, so we're going to want to make sure that we clean that dielectric surface again. We're just going to rotate that swab on the inside with IPA. Make sure that we have the inner threads cleaned as well, and we'll finally hit that with a little bit of compressed air, and we will be all ready to go. You may often use an adapter on your port, and so we're going to want to clean, very similar to the connectors, we're going to want to clean that inner conductor. We're going to want to clean the mating surfaces and inner threads. Probably using one of the swabs. We can also take that swab and clean that inner female conductor around the petals that we had shown previously, making sure that those are clean, as well as the outer threads. And we're going to clean the rest, or after we've cleaned, we're going to spray that off with the compressed air. Adapters are really useful because they protect the input, right? If we damage the adapter, we can simply replace it. Replacing the connector on the front panel is much more expensive, so we would recommend that. Now let's take a look at cable quality. So here we've got a low-cost cable. It's terminating at an N-type on one end, SMA on the other. And we've got a higher quality cable here, also terminating on an N-type on one end, SMA on the other. And so some of the things that we're going to want to look at when we're judging the quality, we want to look at the material type. We want to take a look, are the plating materials quality? Are they flaking or are they solid? We want to look at the conductor. Is that center conductor centered on the dielectric? Is the dielectric good? Strain relief. We want a nice solid strain relief. We want a good feel to the cable. This is a pretty firm cable. Here, the lower quality cable is pretty flimsy around the ends or near the ends, and that's going to. And we also have a smaller diameter, so that indicates that there isn't quite as much shielding or different type of shielding and dielectric in between the shield and the interconductor. So now let's take a look at how those are going to affect our quality of our measurement. Here we've connected up a cable, the higher quality cable, to the signal analyzer. This is a vector network analyzer, the Siglent model SNA 5000, and we have a short open load and through calibration kit, F604FS in specifics. So it's got short open load and through connector element or adapter elements, calibration elements. And this is a really simple test. We're just going to calibrate for S11, which is the reflected measurement. So we're going to look at reflection measurements. We're going to do a calibration, a short open load calibration on port S11 on the cable. So we're going to go through the calibration process, and we're just going to check the stability of the measurement with respect to time, and we'll also shake the cable a little bit. So we're going to go into the calibration menu for the SNA 5000. We're going to select our calibration kit. That is the F604, and then we're going to perform the short open and load test. So we're going to select that out of the menu, and we're going to start the calibration. It's going to prompt us to put the short open and load calibration kit, our elements, onto the cable. So we're going to start with our open, pull that cap off. We've already cleaned this, but we're going to just give it a quick shot to get rid of any dust that might have accumulated. And we're going to turn the barrel of the connector and tighten that. We're not going to spin the actual calibration element. We're going to spin the barrel, and that's going to prevent any damage to that center conductor. We're going to press the open. Once that calibration is complete, we will unscrew the barrel, remove the calibration element, and we're going to move to the short. And so we'll get that element. Here we are with the short, and we're going to then pull its cap off and give it a quick shot with our compressed air. And we will then connect onto the, again, we're spinning the barrel and tightening, and we're going to then press that open button, and we're going to then have that calibration saved. And now we're going to remove that and replace it with the load. This is a 50 ohm load, which matches the characteristic impedance of the spectrum analyzer input, or vector network analyzer input. Again, we're going to tighten the barrel, and you'll see that S11, or the reflected value, is going to change there. We're going to calibrate to that load. Once that's complete, we will accept the calibration state, and we will now switch the view over to the Smith chart and complex impedance with the Smith chart S11. And you'll see the characteristic impedance is this little yellow dot in the center with a 50 ohm load, and that is a very good calibration. You'll see as we shake the cable, that is not changing at all. And this is a sweep over 8.5 gigs. So now let's connect the other cable, and we're going to see immediately that there is quite a bit of a difference on the Smith chart. Let's do the calibration very quickly. Short open load. And once we've finished that and accepted it, we could take a look. Now we've got that characteristic impedance in the center again, that's the 50 ohm point, but you'll see it's much bigger. And as we move the cable, you can see that there's quite a bit of instability, a lot of changes over time as we reposition that cable. And what that means, if we are to calibrate this using this cable, any changes to that cable's position could very well change that reflected measurement, and that could be problematic for us as we go forward. I'd like to close by summarizing. We want to visually inspect the cable and adapter quality, and we want to verify the concentricity of the center conductor, the depth and cleanliness of the connector dielectric, We want to check the cable armor for any fraying and also a good feel. We want it to be linear. We want to, as we move the cable, we don't want kinks or anything like that. We want to look at that conductor and connector plating quality, see if there's anything flaking off. And then we want to take a look at that strain relief. Has it been overused? Is it starting to break down? That's going to indicate that the dielectric inside may also, and the shielding inside may also be frayed. The test cable effects on measurement stability. We want to test that. We could simply connect the cable using that S11 Smith chart measurement type. We can perform a short open and load calibration, and then we can just view the stability. As we shake the cable or move the cable around in different ways, is that 50 ohm point on the center of that Smith chart moving around excessively? That's going to indicate that we may have some cabling issues.